Okay, in this class we discuss the properties of measure. M is measure. The Lebesgue pair of measure M is first the properties. M is countable additive. What is the meaning of a set function is additive? If we have a countable class of disjoint sets, the value of the union is the sum of value of individual sets. So here M is the set function, which is countable additive means if we have a countable class of disjoint measurable sets, measure of union En is sum of M of En. Here the main thing is the sets must be mutually disjoint. Right? Then we can separate the measures. If you want to find the union of measure of union of two sets, if the two sets are disjoint, then you can find the independent individual set measure and you can add it. Okay, so now we prove that. Already we have, when we prove the theorem stat, if countable union of measurable sets are measurable, we have proved the following, right? So we recall the proof of the result that the result is countable union of measurable sets is measurable. Is measurable. Okay, so we briefly see that proof. So first thing, let us take E and be the countable class of measurable sets. Countable class of measurable sets. Here we assume the measurable sets are mutually disjoint. Mutually disjoint measurable sets. Then, as in the proof of this result, we start. Let us take let A be any arbitrary set. This is the proof exactly the same as the proof of the result, the above result, but we change a little bit. Arbitrary set. Then we prove that M star of A greater than or equal to M star of A intersection E1 plus M star of A intersection E1 complement. Then apply, we have applied the definition of measurability, E1, measurable set. We keep the first term as it is. The second is MA E1 complement intersection E2 plus M star of A intersection E1 complement intersection E2 complement. Yeah, in that M intersection E1 complement E2 measurable apply right? So similarly, here the last term can be written as the first term as it is, as second term is also same. The last term is A intersection E1 union E2 complement. So then we apply the measurability of E3 in the last three equation. Then we obtain the following: M star of A intersection E1 plus M star of A intersection E1 complement intersection E2 plus M star of A intersection E1 union E2 complement intersection E3 plus M star of A intersection E1 union E2 complement intersection E3 complement that term is exactly this. A intersection E1 union E2 union E3 complement. Okay. So at the nth stage, so we have the following equation. Nth stage is equal to summation n from 1 to infinity. Yeah, k from 1 to infinity, 1 to n star of A intersection E intersection j less than k, Aj intersection Ak, sorry, Ej complement intersection Ek, plus m star of A intersection union k from 1 to n Ek complement. Okay, this is it. Okay. Then which is greater than or equal to, first term is as it is, summation k from 1 to n star of A intersection j less than k, Ej complement intersection Ek. So the last term is replaced by A intersection k union k from 1 to infinity, k from 1 to infinity Ek complement. Here this union k, here we have only E1 E2 up to En. Here we have infinitely many sets, right? So only the members of A which are in union of finitely many sets is removed, but here infinitely many removed. So obviously, okay, the set appearing in the first equation is bigger than this set. So outer measure obviously is smaller for the second. So this is applying the limit we have, which is m star of A as n goes to infinity. So m star of A is greater than or equal to summation n from 1 to infinity m star of A intersection union j less than n Ej complement intersection En, plus m star of A intersection union k from 1 to infinity Ek complement. Okay, this up to this we have, okay, you have followed the proof of the above mentioned theorem. Yeah, அந்த தியரமோட ப்ரூஃப் தான் எக்ஸாக்டாக ஃபாலோ பண்ணிட்டு வரேன். நீங்கள் அந்த ப்ரூஃப் ரெஃபரன்ஸ் பார்த்துங்க, ஏற்கனவே நோட்ஸ் கொடுத்தோம் இல்லையா. ஓகே, இப்போது இந்த இடத்துல இந்த செட் எக்ஸாக்டாக எப்படி இருக்கும், ஆக்சுவலாக எப்படி இருக்கும், விச் இஸ் கிரேட்டர் ஆர் ஈக்குவல் டு En அப்படின்னு எழுதிட்டு போகணும். பட் நான் இந்த இடத்துல என்ன பண்ணுறேன், இந்த இடத்துல நம்ம அசம்ஷன் வந்து EAs ஆர் மியூச்சுவலி டிஸ்சார்ஜ். இங்கே let us take A, this is true for any A, right? So let us take A equal to union n from 1 to infinity En, right? Then the above inequality become m star of union En n from 1 to infinity, which is greater than or equal to summation n from 1 to infinity m star of union n from 1 to infinity En intersection union j less than n Ej complement intersection En, plus last term A is union of En intersection union En complement. So intersection is empty, outer measure is 0, so that term will disappear. So only we have this. Now we evaluate this set one by one. Okay, this is equal to m star of, at each term we have n from, before okay, instead of writing this we okay, find this set. Okay, this is equation number 280. Now union n from 1 to infinity En intersection En. Actually, I have to change the notation. Here I take k. K from it. K, this is k. Here we have k from 1 to infinity. Okay. So I take k. K from 1 to infinity ek at intersection En is En is one among the set in the union, so this is exactly En. Right? And since this collection En is disjoint, mutually disjoint. So, okay, En intersection Em is empty and n not equal to. Okay, so not in particular. So different index different sets and the different set intersection empty, yeah, right? In particular, if for j less than or equal to k, for j less than k less than n, ej intersection En empty. Only for j smaller than n, which implies Ej complement contains En for j less than n. Okay, it means union j less than n Ej complement actually I write this. This is it. Intersection is empty. That's right. This is intersection Ej cut Ej complement. Ej complement contains E for j less than n. For all j, right? For all j less than n. This is for all j less than n. J n को do. Intersection level only, j complement j less than n contains En. Right? So theoretical property for j less than n, Ej whole complement contains E. Okay, En. So this implies that if we take the intersection of this set and the En, then result is En. Union j less than n Ej complements intersection En. This En, the subset comes in the intersection. Also here you see intersection is En. Right? Here no need to write intersection. This I write, this is a subset of. I write here this contains En. Right? And also here En Ej complement contains En. So En contained in union En, union Ek, En contained in union j less than n Ej. So implies En contained in union k from 1 to infinity En Ek intersection union j less than n Ej complement. So now what is the intersection of these three sets? The moon set intersection union k from 1 to infinity Ek intersection union j less than n EJ complement intersection EN. The result என்னவா இருக்கும்? EN. இல்லையா? எல்லா செட்லயும் இருக்கிற எலமெண்ட். EN இந்த ரெண்டுக்கும் சப்செட். அதனால intersection EN அதான். ரைட்? இந்த நம்பர் என்னன்னா இந்த லாஸ்ட் டேர்ம் ஈக்குவேஷன் 2ல வர்ற m ஸ்டார் உள்ள இருக்கு இல்லையா? அங்க. ரைட்? என்ன ப்ரூவ் பண்றோம்? from 2 m star of union ek k from 1 to infinity is greater than or equal to summation n from 1 to infinity m star of the in equation 2 the right hand side set is this, that is equal to E. Okay, so therefore we change the index here now, summation n from 1 to infinity m of En. We have obtained that summation n from 1 to infinity. Sorry, not summation, it is union of m of union. Here I have no need to write here m is right m. Thus En is measurable, union of En is measurable. Shows m of union n from 1 to infinity En. Okay, this is equation number 3. Already since already we know that outer measure is countable subadditive, so all the properties of outer measure, okay, is valid for m also. So since m star is countable subadditive. So m of union n from 1 to infinity is less than or equal to summation n from 1 to infinity m of En. Equation number 4. Right? So proof on the superadditive. Equation 3 says that m is superadditive and the subadditive. So it's countable additive. From combining 3 and 4, we get m star m of union n from 1 to infinity equal to summation n from 1 to infinity m of E. Right? Therefore m is countable additive. Okay, புரிஞ்சுதா? Only simple thing, இந்த ரிசல்ட்ல a க்கு பதிலா என்ன சப்ஸ்டிட்யூட் பண்ணிருக்கேன்? யூனியன் ek அவ்வளவுதான். for any set that result valid, so union ek substitute பண்ணி we apply, okay, we use the fact that En are, okay, mutually disjoint. So disjoint class. So class of mutually, write this sentence is class of mutually disjoint. So class of mutually disjoint sets. Okay, that's what we use this fact to say that the set obtained in the equation 2 is exactly En. Okay. So next corollary, if A and B are measurable, okay, such that A subset of B, then so m star of A minus B is m or B minus A. A subset of B, so B A minus A empty, right? B minus A is m star of B minus m star of B. Here we write only m of B, because A, B are measurable, so m star is nothing but m of. And if you have two sets measurable, their difference is measurable. So B minus A is also measurable. So we write the result that m of B minus A is m of B, m of A. Then what is the definition of B? B minus A is the difference set of all B which are not in E. Okay, earlier we used the notation that B, this notation, B difference A. We use this notation. Any notation can be used, but we follow Barra book, so I am going to use this notation. Right? This also equal same. Undefined. Okay, same notation. Usual notation is this, but we follow this notation. Right? So to prove the corollary, we are going to use the countable additivity of M. எப்படி ப்ரூவ் பண்ணலாம்? ப்ரூஃப் ஐடியா சொல்லுங்க பார்க்கலாம். எஸ், இந்த ஈக்குவேஷன் வந்து கொண்டு வந்துடலாமா? கவுண்டர் இந்த ஏ இந்த பக்கம் கொண்டு வந்துடுறேன். ரைட், இது ஈக்குவேஷன் எப்படி எழுதலாம்? எம் ஆஃப் ஏ பிளஸ் எம் ஆஃப் பி மைனஸ் ஏ. ரைட், so countable additive property says that if A and B minus A are disjoint, then you write the union M of A union B minus A. Right? A union B minus A is exactly B. Right? So that comes, that result comes. Okay. Clear? Right? Proof and since A subset of B, so B can be written as A union B minus A. Where? So here set of all B elements of B not in A. So any element, okay, any element sitting in this A not in B minus A. So these two are mutually disjoint. Okay, clearly. A intersection B minus A is empty by the definition of the constant empty. So by the countable additivity of M, we write M of B equal to M of A plus M of B minus A. So now we shuffle the terms so that M of B minus A equal to M of B minus M of A. Okay, so when the set or difference are picture, when A is a subset of this only, this is happens when A is a subset of right. This is a general set adutha corollary. Suppose A, B are any two sets. If A and B are any two sets, any two measurable sets. Right. Then suppose this is A, suppose this is B. Right? This A union B can be written as P sets, right? One set is, this is A minus B, this is B minus A, this is A intersection B. Right? So we are going to write the property as follows. Then M of A union B is M of B minus A plus M of A minus B plus M of A intersection B. The next definition, we know the definition of symmetric difference of two sets, right? There's a definition of symmetric difference. This is called symmetric difference. Symmetric difference na A symmetric difference B in the set in the set சேர்ந்தது, right? A minus B union B minus B. The relation of the symmetric argument B minus B symmetric difference A same set, right? Okay, na theriyum fact A difference B, A symmetric difference B is B symmetric difference. So the property is symmetric. இந்த ரெண்டு கடையில ரிலேஷன் வந்து symmetric. ஓகே, இப்போ இந்த கரலரி 2 வந்து ரீரைட் பண்ணிக்கலாம். எப்படி? நெக்ஸ்ட் கரலரி if A and B are measurable, then M of A union B is M of A symmetric difference B plus M of A intersection. Okay. The next is the result. If A is measurable, and B is any set such that M star of A symmetric difference B equal to 0, okay, then for stating this, we give some elementary results about, okay, the measurability. If A is any set, okay, with whose outer measure is 0, with the 0 outer measure, set of 0 outer measure, then A is measurable. That is, if M star of A is 0, then A is measurable. So we use E notation, E. So take E as a set. Proof is very simple. So to prove that E is measurable, so we have to take an arbitrary set contained in R. Then we have to prove that M star of A is greater than or equal to M star of A intersection E plus M star of A intersection E complement. But here in this case we can directly prove that this is equal. Okay, the proof is left as exercise, right? Leave it to the exercise. Leave it as exercise. Simple trick we use, right? Okay, இது நாளைக்கு கிளாஸ்ல டிஸ்கஸ் பண்ணுவோம் இந்த எக்ஸசைஸ். இதே எக்ஸசைஸை கூகுள் கிளாஸ் ரூம்ல போஸ்ட் பண்ணிடுறேன், நீங்க டிஸ்கஸ் பண்ணி பாருங்க, சால்வ் பண்ணி பார்க்கலாம். Okay. Next result, we are going to use the result, this result, right? If M star of E is 0, then E is measurable. The result, if okay, A is measurable and B is any set such that outer measure of A symmetric difference B is 0, then B is also measurable. Proof. So very simple. Proof is very simple. The previous result says that if a set has outer measure 0, then that set is measurable, right? by the previous results. Okay, yeah, B delta A delta B measurable. Not only this, A difference B and B difference A all are measurable. Okay. Why? Because M star of A difference B is subset of A delta B. So this is less than or equal to A delta B is 0. It's greater than or equal to. So M star of A minus B is 0. So A minus B is also measurable. Here we are going to, okay, the idea of the proof is this set is measurable, right? A is measurable and the lined portion has 0 measure. Now I am going to prove that we know that this is the B minus A is measurable, right? This checked portion is measurable. If you prove that A intersection B is measurable, then the union of these two measurable. So we have to prove A intersection B is measurable, right? So now we write A intersection B as a complement of these two. Or you write from the A we remove this portion. Okay, this portion and okay, we get this. So by the set theory property, we have A intersection B equal to A difference B. In the whole A, we remove this A difference B. This A difference B is removed from whole A, we will get this. Already A measurable, A minus B measurable. So A minus B, A minus B is measurable, right? So this since we know that A intersection B is this. Right? So this implies that A intersection B is measurable. Then finally you write B as a intersection of union of A intersection B union B difference A. Right? This set and this set. Okay? This combined, this whole thing is A intersection B and B minus A. So A intersection B measurable, already we know B minus A measurable, therefore B is measurable. So if we have immediate corollary of result, if A is measurable and B is a set such that M star of whether we don't know whether B minus A is measurable and outer measure of B minus A is 0, then B is measurable. Okay, these are the very simple properties we frequently use in the forthcoming discussions. Okay. இதுவரைக்கும் ஏதாவது டவுட் இருக்குதா? எல்லாமே பின்னாடி யூஸ் பண்ணும். என்னென்ன ரிசல்ட்லாம் இப்போ பார்த்துருக்குறோம் ஒன்று பார்க்கலாமா? ரீகால் பண்ணுங்க. ஃபர்ஸ்ட் ஒன்று என்ன? கவுண்டபிள் additive property, not separate. Countable additive property na, if we have mutually disjoint measurable sets, okay, the countable class of mutually disjoint measurable sets, then M of union En is summation M of En equal. Okay, this mutually disjoint எல்லாம் இருந்தா the less or equal inequality மட்டும் அதை கம்பேர் பண்ணிக்கிறோம் ஞாபகம், right? அதுக்கு proof பார்த்தோம். அடுத்த ரிசல்ட் என்ன? Suppose A and B are measurable, A subset of B, then M of B minus A என்கிறது M of B minus M of A னு பிரிச்சு எழுதிக்கலாம். A B இந்த இடத்துல லெஃப்ட்ல வர B minus A னா இந்த இடத்துல வர B minus A வந்து இந்த மைனஸ் செட் ஆபரேஷன் ரைட் டிஃபரன்ஸ் இந்த மைனஸ் என்ன இங்க ரெண்டு ரியல் நம்பருக்கு இடையில வர சப்ட்ராக்ஷன் ரைட் இது செட் டிஃபரன்ஸ் இது சப்ட்ராக்ஷன் ரைட் அந்த டிஃபரன்ஸ் இருக்கு பட் எனிவே தி m of B minus m of A அப்படினு எழுதிக்கலாம் m of B minus A ஓகே அடுத்தது if A B are measurable இப்படி பிரிச்சு எழுதிக்கலாம் அதோட கான்சிக்வென்ஸ் அதான் ஓகே எங்கெல்லாம் ரெண்டு செட் மியூச்சுவலி டிஸ்ஜாயிண்டா இருக்கோ அதோட மெஷர்ஸ் ரெண்டா உடைச்சு சம்மா எழுதிக்கலாம் இல்லையா ரைட் ஓகே இந்த இடத்துல ரொம்ப இம்பார்ட்டன்ட் ரிசல்ட் என்ன if m star of E is 0 then E is measurable okay ஒரு செட்டோட அவுட்டர் மெஷர் 0 ஆ இருந்தா அந்த செட் மெஷரபிள் ரைட் அதே இது ஒரு செட் மெஷரபிள் இன்னொரு செட்டோட symmetric difference with the measurable set is 0 has measured 0 and that set itself measurable right ஒரு measurable செட்டுக்கும் இன்னொரு செட்டுக்கு இடையில டிஃபரன்ஸ் 0 மெஷர் அவுட்டர் மெஷர் 0 ஆ இருந்தா இன்னொரு செட்டும் measurable ஓகே இதற்கு ஏதாவது டவுட் இருக்குதா if you have any doubt please unmute and doubt இல்ல அப்படிதானே ஒரு ஆளு unmuteல வந்து சொல்லுங்க ஓகே அட்லீஸ்ட் சாட் பாக்ஸ் வாங்க பார்க்கலாம் okay so next concept we defined limit supremum limit infimum of the sets right okay so we consider the sequence of sets consider let En be a sequence of sets then define following limit supremum n goes to infinity En. This is nothing but intersection n from 1 to infinity okay of the following set. That set is union k greater than or equal to n ek and limit infimum En n goes to infinity is you don't to write that n goes to infinity. Limit supremum En is this. Limit infimum is union n from 1 to infinity intersection k greater than or equal to n ek. Okay. So one thing is clear that note. It is clear that limit infimum En always less than or equal to limit supremum. Okay. In second definition, we write the limit of the sequence here. Okay, define if limits infimum En equal to limits supremum En, then the common values defined as then we see that limit exists. Then we say that limit En exists. Right? And the limit is the common value of just, and is the common value of limit infimum En and limit supremum. Okay. So what's the meaning of this limit supremum? As in the sequence எப்படி படிச்சிருக்கோம்? Limit supremum for a sequence of numbers. Suppose an is a sequence of numbers, sequence of real numbers. What is limit supremum an? We separate this limit and supremum. Limits of supremum an. Right? How do you find this supremum as? Okay, n goes to infinity this way. N goes to infinity. Okay. Okay. For different nm, if m is bigger or n is smaller, n smaller, then this set is as n goes in n increasing, the supremum ak increases. So actually supremum decreases, right? So as n increases to infinity, supremum ak k greater than or equal to m decreases. So limit infimum will be the limit of this. So it can be replaced by infimum over n, supremum k greater than or equal to n ak. So this is the definition of this. And similarly, we write these limits infimum an. This is supremum over a over n. Infimum k greater than or equal to n ak. So one thing is clear here that the infimum is the greatest lower bound, supremum is the least upper bound. So for any sets, infimum ak k greater than or equal to n for any n, or for the any set, infimum value is always less than or equal to supremum k greater than or equal to n ak. Right? This is true for any, but an okay, this is suppose I define this as bn and this is cn. Bn always less than or equal to cn for each n. Right? So not only this, for any two integers, first any nm, infimum ak k less than or greater than or equal to n is always less than or equal to supremum k greater than or equal to n ak. We take two different indices and infimum is always less than or equal to supremum. Right? Here I am going to take the infimum, and so you don't need to write this. You actually have a detailed explanation. We see later. We don't want a big explanation, but anyway. Actually, this infimum ak less than or equal to supremum ak, right? So once I fix n for infimum and vary okay n for supremum, always this infimum less than or equal to all the supremum. So we take supreme, okay, infimum value among this value, always this is less than to this. The supremum of this less than or equal to. So limit infimum an less than or equal to limit supremum a. If equality exists, if I take this limit, if limit infimum an equal to limit supremum an, then sequence an is said to converge. Said to converge. And the limit is defined as, okay, and the common value is the limit. Value is defined as the limit. Limit of the sequence A. Okay, this is a basic okay definition. We can define the convergence of the sequence in the in this way also. Okay, but we write this limit supreme infimum for the sets, okay, and we define this. Okay. So now we have the following theorem. If En is a sequence of measurable sets, let us take this. Let's En be a sequence of measurable sets, then number 1, if E1 contained in E2 contained in E3 and so on, if the sequence is increasing, then measure of limit En is equal to limit of measure of E. Measure of E. Limit of measure of E. The second one, if E1 contains E2, contains E3, etc., it's a decreasing sequence, and then the measure of the largest set E1 is finite, then limit measure of limit En is limit measure of E. So measure and limit can be interchanged, right? So the correction in the result discussed in this, okay, இந்த இடத்துல டிஸ்கஸ் பண்ணிக்கிறோம் v minus a எழுதும்போது இந்த இடத்துல டிஸ்கஸ் பண்ணோம் இல்லையா, இந்த இடத்துல ஒரு கண்டிஷன் ஒன்று எக்ஸ்ட்ரா சேர்த்துக்கிறேன். என்னன்னா AB are measurable and the measure of B வந்து finite இருக்கும்போது, or either ரெண்டுல ஏதாவது ஒன்று finite இருக்கும், ரெண்டுமே infinite இருந்தால் இது undefined இல்லையா, either measure of A is finite or measure of B is finite. இப்படி இருக்கதான் இது true, right? ஏன் அப்படின்னா சப்போஸ் ரெண்டுமே இன்ஃபினிட்டியா இருந்தால் இன்ஃபினிட்டி மைனஸ் இன்ஃபினிட்டி எழுதும், ரைட்? அந்த எழுதக்கூடாது. மெஷர் ஆஃப் பி மைனஸ், ஓகே, அன்டிஃபைன்டு, இன்ஃபினிட்டி மைனஸ் இன்ஃபினிட்டி. அதனால என்ன கண்டிஷன் எடுத்துக்கிறேன், இதோட பியோட மெஷர் ஃபைனைட்டாக இருந்தால் ஏக்கு மெஷர் ஃபைனைட் தான், அதனால தனித்தனியாக சொல்ல தேவையில்லை. மெஷர் ஆஃப் பி ஃபைனைட், யா கரெக்ட். இது ஃபைனைட், இது இன்ஃபினைட்டாக இருக்கலாம். பிக்கு இன்ஃபினைட் மெஷராக இருந்தால் ஏக்கு ஃபைனைட் மெஷர் இருந்தாகும். சப்போஸ் பிக்கு ஃபைனைட் மெஷர் இருந்தால் ஏக்கும் ஃபைனைட் மெஷர் தான், ஏன்னா அவுட்டர் மெஷர் ஃபைனைட் தானே, அதனால் ஏதாவது ஒன்று எழுதிக்கலாம். either m of a is finite or m of b is finite. ரெண்டுல ஏதாவது ஒன்று இருக்கும்போது then we have this result, right? Then m of b minus a is m of b minus m of a. Okay. Okay, இங்க வந்து காமனா என்ன பண்ணா m of say first side I write such that m of a union b finite measure ஆ இருக்கும்போது இப்படி எழுதலாம், right? நான் m of b minus a எழுதும்போது m of b minus m of a எழுதுவோம், இது ரைட். இந்த சைடு கொண்டு வரும்போது நெகட்டிவ்ல வரும், இன்ஃபினிட்டி மைனஸ் இன்ஃபினிட்டின்ற சிச்சுவேஷன் அவாய்ட் பண்ணுவோம் அதுக்காக, ரைட்? அது இப்போதான் ஞாபகம் வந்து. ஓகே ஓகே ஸோ எனிவே ஸோ we prove the first part of using countable additivity. Okay, given that given that E1 contained in E2 contained in E3 and so on. Okay, now countable additivity use பண்ணுவோம். இந்த increasing sequence of set ல இருந்து ஒரு disjoint collection நான் எடுக்கும் இல்லையா? அப்போ நான் என்ன பண்ணலாம்னா E1 ஒரு செட், இதை நான் F1 எடுத்துக்கிறேன், ரைட்? E2 contains E1 இல்லையா, ரைட்? இந்த டிஃபரன்ஸ் இருக்கு இல்லையா, ரைட்? F2 எப்படி எடுத்துக்கிறேன்னா members of E2 not in E1, இந்த gap, ரைட்? அது வந்து F2 ன்னு எடுத்துக்கிறேன். F3 என்ன எடுத்துக்க போறேன்? F3 is going to be E3 minus E1, E2, right? E2. இப்போ இந்த செட் disjoint F1 disjoint from, so F1 is nothing but exactly E1, F2 is E2 minus E1, F3 is E3 minus E2 and so on. The F1 is different from F2, F2 different from F3, okay, F3 is different from F1 also. So we continue to prove define this way. We have the following. So let's F1 equal to E1, and for each n from 2 to 3 etc, Fn equal to En minus En minus 1. Then clearly for any m less than n, what about Fn intersection Fn? Fn is Fm is Em minus Em minus 1, right? Fm is a subset of Em, right? This is Fm intersection here En minus En minus 1, right? The m is smaller, so it's a subset of this. Fm is a subset of Em, right? Intersection En. What about En minus 1? En minus m is here we assume that m is less than n, m less than or equal to n minus. So by the assumption Em contained in En minus 1, right? What about En minus Em, which contains En minus En minus 1? Okay. Okay, so we look at this. Members of En but not in EM. Right? Once the element is not in EM minus 1, it's not in EM. So this is subset of, so in the place of En minus 1, we have En minus EM. Right? The right hand side set is the element, is a set of all elements in En, not having any, okay, not in EM. But here only EM, so this is empty, right? This is exactly empty set. So Fm intersection Fn is subset of empty set, means Fm intersection Fn is empty. Okay, for any m less than. Therefore, for any m not equal to n, Fm intersection Fn is empty. So this says that Fn is a class of mutually, and Fn are measurable, right? By the definition, Fn are measurable. Okay, since Fn is En minus 1, and all the Ens are measurable. All the En are measurable. So Fn is measurable. Difference of two measurable sets measurable. Fn measurable, right? Fn collection Fn is a sequence of mutually disjoint measurable sets. Okay. Then what about the union of E? Right? Union of E. N from 1 to infinity now. N from 1 to, okay. Now we apply the measurable, okay, countable additivity of M on Fn by, okay, since M is countable additive, M of union Fn, n from 1 to infinity, is equal to summation n from 1 to infinity M of Fn. Now we evaluate the left hand side and the right hand side values. Okay. So now take this as equation number 1. So union Fn, n from 1 to infinity. This is union n from 1 to infinity. But we prove by induction, right? You evaluate the limit of the set. So this I am going to write, this is the limit of En, right? Now we claim that for n from 1 to infinity, Fn is n from 1 to infinity. For that we can easily, okay, prove that 1 is a subset of 1. Since Fn subset of En, so union n from 1 to, this implies Fn contained in union E. Okay, to prove the other inequality, let us take x belongs to union En, n from 1 to infinity. Then x belongs to En, Ek for some k. Okay. Which means that x belongs to you write En for some n. When x belongs to, then we choose a minimum, smallest n, such that choose let n not be the smallest positive noun integer, such that x belongs to okay En. X வந்து the union எல்லாத்துலயுமே இருக்கும் இல்லையா, யூனியன்ல இருக்குன்னா ஏதாவது ஒரு செட்ல இருக்கும். X belongs to one or more sets, right? So we choose the smallest index such that x belongs to, right? Then this means n0 is the smallest number, so x does not belong to En0 minus 1. So this implies that x belongs to f n0. Means x belongs to union f until infinity. So therefore union En from 1 to infinity is contained in union f and n from 1 to infinity. Therefore union of fn is union En. Okay. For the increasing sequence of sets, En of sets, okay, limit En is exactly union E. Okay, therefore limit En is union Fn, n from 1 to infinity. Okay. So therefore now from to measure of limit En equal to measure of union Fn, n from 1 to infinity, by the countable subjectivity summation n from 1 to infinity m of union Fn, m of Fn. Okay, this is equal to limit n tends to infinity summation k from 1 to n m of fk. Okay, so we consider this is a limit of the sequence of parcels. Now again by the countable additivity, this can be written as m of union fk, k from 1 to n. Okay, this is equal to limit n tends to infinity, so m of, right, union ek. Okay, this can be proved using induction. Okay, here we have used that fk, k from 1 to n equal to union k from 1 to n ek. Okay, use induction to prove, use method of mathematical induction, math induction. Prove the equation, right? To prove. So we use that. Again we use, okay, countable additivity. We have summation k from 1 to n m of ek. which is a partial sum of the limit of the partial sum. So I take n from 1 to infinity m of e. That's all the proof. Okay. So second part is very simple and followed by the first part, proof of part 2. So we have that m of E1 finite and E1 contains E2 contains and so on. If we write this decreasing sequence of sets in terms of increasing sequence by taking the difference, right? First we start with E1 difference E1. This is empty set, which is a subset of E1 minus E2, subset of E1 minus E3, and so on. So for that we define F1, F2 and so on. So using this idea, define Fn equal to E1 minus En, n from 1, 2, 3 and so on. So clear that F1 contained in F2, otherwise it is Gn. G1 contained in G2, contained in so on. Right? Then by part 1, write measure of limit Gn equal to measure of G. So now we find a measure of limit Gn and limit of measure G. Now what about limit of Gn? This is by the definition limit E1 minus En. Right here we separate the limits, and then this limit is Gn is increasing, so the limit is written as union of G, union Gn, n from 1 to infinity, right? So union n from 1 to infinity by a definition E1 minus En. This is equal to, by the set theory law, this is intersection n from 1 to infinity En. Right? So since measure of E1 is finite, so measure of limit Gn equal to measure of E1 minus intersection En, n from 1 to infinity, equal to measure of E1 minus measure of intersection En from 1 to infinity. Here En are decreasing, so the intersection is the limit, m of E1 minus m of limit En. So I am going to take this as equation number 2 in this theorem. This equation number 3. Now we limit a tends to infinity, we write m of Gn. So by the definition of Gn, this is m of E1 minus En. We know measure of E1 is finite, so we can split the measure by the following way: measure of E1 minus measure of En. The m of E1 is a constant, so limit m of E1, m of E1 minus limit n tends to infinity m of En. Right? This is equation number 4. From 2 to 4, from 2, 3, 4, we substitute 3 and 4 in equation number 2. We have m of En E1 we have m of E1 minus m of limit En equal to m of En minus limit m of En. So cancelling m of E1 and minus 1 from this second one, we have m of limit En equal to limit m of En. Okay, that's all the proof of equation part 2. Okay, here one thing is okay. This left us exercise. So what is that? If E1 contained in E2, exercise for the previous. Okay, we are part in this. Limit of En is union En from 1 to infinity. Okay, we show that. If E1 contained in E2, contained in E3, and so on, show that limit of En is intersection E. The limit எப்படி கண்டுபிடிப்பீங்க? இந்த சீக்வென்ஸ்க்கு லிமிட் சுப்ரீமும் லிமிட் இன்ஃபிமம் கால்குலேட் பண்ணணும். ரெண்டுமே ஈக்குவலா இருக்கணும். அந்த ரெண்டுமே இந்த ஃபர்ஸ்ட் பார்ட் ஆஃப் எக்ஸசைஸ்க்கு யூனியனா வரணும். செகண்ட் பார்ட் ஆஃப் எக்ஸசைஸ்க்கு வந்து இன்டர்செக்ஷனா வரணும். லிமிட் சுப்ரீம். இது எப்படி கண்டுபிடிப்பீங்க? எக்ஸசைஸ் எப்படி சால்வ் பண்றது? ஃபைண்ட் லிமிட் சுப்ரீமம் En, அதாவது யூனியன் இன்டர்செக்ஷன் n from 1 to infinity union k greater than or equal to n ek calculate பண்ணனும். limit infimum En எப்படி calculate பண்ணனும்? union n from 1 to infinity intersection k greater than or equal to n ek. ரெண்டுமே calculate பண்ணனும். calculate பண்ணா first exercise க்கு union வரும். union E. second exercise க்கு intersection. இது நான் உள்ள யூஸ் பண்ணிருப்போம் ஒரு இடத்துல. அதான் நீங்க செட் தியரி சிம்பிள்னால செட் தியரி ரிசல்ட் தான். அதனால இது நீங்கள் ஈஸியாக ப்ரூவ் பண்ண முடியும். ஓகே, இது நாளைக்கு பார்க்கலாம். தேங்க்யூ.